Today's video is the first in our series for Unit 2, which is entitled What is Chemistry? Matter and Energy. Today we're going to look a little bit at energy. We're also going to kind of ask the question, what is chemistry, and try and answer that in terms of where does it fit into our sciences and how does a science like chemistry work and what's it all about. So we'll start out by answering the question, what is chemistry? Basically, chemistry is this. It's the study of matter. And not just the study of matter like categorizing matter and figuring out how to name it, which is part of what chemists do, but also two important questions. How does it change? That's very important to chemists. And why does it change? Those are two fundamental questions that chemists have been asking for generations and will continue to ask. Chemistry sometimes is called the central science. In fact, there's a very famous college chemistry book that's named the central science. And here's why. Because on the one hand, the very tiny particles that make up everything that exists in our world and the energy that kind of binds them together and causes them to move around and behave the way they do, that's the study of physics. When the particles get so complicated that they're part of living things, that's biology. In the middle is chemistry. And chemistry kind of bridges the gap between this very fundamental understanding that we get in physics and this very complex understanding that we have in the science of biology. Chemistry, like all science, is operated according to the scientific method. And the scientific method is sort of an idealized way that we sort of wish that science always happened. And in fact, over the long haul, this really is how science develops knowledge. But in the short term, sometimes there are deviations. These are the basic ideas. First of all, there's an observation. Someone has to observe, to see something. Somebody notices something. This is sometimes done in a lab or in the field as part of a formal study. Sometimes it's just pure accident. Somebody stumbles onto an observation. And scientists, it turns out, are particularly good at observing things that other people might not even think to look for. Often these observations involve more than just one measurement, two measurements happening at the same time. The next step is, after observing for a while, scientists start to see a pattern develop. And the step where we describe that pattern is called a generalization. We generalize. So scientists are always looking for these kinds of patterns and describing them. And there are some patterns that happen so often and never seem to ever have a failure. They always seem to fit and always seem to work. Those things sometimes come to be called laws. And you've probably learned some of these laws of science in other science classes when you were younger. Generalizing just describes the pattern, and then the next step, and this is where the scientists really get excited, is trying to come up with an explanation or a theory. So this is called theorizing, this step. Scientists always assume that there is going to be an explanation, and so they look for it. They try and find out what it might possibly be. If a theory hasn't had a chance, if an explanation hasn't had a chance to become tested, it's called a hypothesis at first. But after it passes a few tests and seems to become fairly reliable and makes good predictions about what will happen in the future, then it becomes called a theory, and it's a little bit more solid. Once a theory is present, the next thing we want to do is test it, and that's the next step in the scientific method. Now, you will set up a test so that if your theory is right, the test will be passed. If your theory seems to be wrong, the test will show that. It will fail. But a passed test does not necessarily mean that the theory is true. And I put true in quotation marks here because that's not really a word that scientists are really into. We consider observations to be true. Those are facts. But our theories are works in progress. We always understand that they're going to be modified, that they're going to be changed and updated as we gain more information. So a past test might make things seem like it's a better explanation, and it might gain some weight, and we might come to think about it as being true, but we don't call things true just because they passed a scientific test in science. A failed test is just an observation, and that observation starts this cycle all over again. So if you fail a test, you've noticed something. That's an observation. You can make a new generalization that's better, that includes more information, create a new theory that explains the new generalization, and then test that theory. And this cycle that continues to go on and on and on is how science develops the knowledge that it has. Sometimes scientists can accidentally jump into the cycle at any given step. Another thing is that there are some scientists that spend their entire careers at just one step. Some people are just observers. All they do is write down observations and generalizations. Some people just create theories based on other people's generalizations, and they can spend an entire career doing that. And some people are just testers. They take other people's theories and they apply many, many tests to them to try and show if they're valid or if there needs to be a refinement. So it's not like a scientist wakes up in the morning, observes, generalizes, theorizes, tests, and then goes home for the day. It's a long-term process, and it often involves many, many people making some of the same observations and theories and tests. The next focus here that we're going to take is on energy. Energy isn't really the primary focus of chemistry. We're more about matter, which we'll talk about later. But we need to use the idea of energy to study chemistry properly because there's such an important interplay between matter and energy. So energy really isn't a thing. Energy is an ability or a potential. It's kind of this latent hope almost that something can happen. And there are two things that can happen because of energy. One is a change in temperature might be observed. And then the second one is you might have the ability to do work. Now a change in temperature means, it gets hotter. What does it mean to do work? It doesn't mean that you punch a clock and get paid for it. That's kind of a common everyday description of what work is. But in science, work actually means that there's going to be a change to some matter. Specifically, it means that force is going to push something through a distance. Energy can be stored in the motion of an object. And we just saw that the energy that was stored in the motion of that ball did some work on that block wall. Here's the ball. Same ball hits the block wall, and it doesn't do work on the wall. But the wall heats up a little bit, and so does the ball. And so there's a temperature change. So the energy that was stored in the motion of that ball caused work or caused a temperature change. That's one of the ways that energy can be stored, in the motion of an object. When energy is stored in the motion of an object, we call that kinetic energy. It's kind of a label for that storage mode of energy. Kinetic energy sometimes we see in the motion of large objects like a ball or a car or an airplane or a bullet. But we also can see kinetic energy in heat, which is really just the chaotic, random movement of tiny objects like atoms and molecules. As they jiggle around, their translational kinetic energy, we think of that as heat. Another way that kinetic energy can be stored in motion is sound waves. And that's just motion of waves of material like air or water or even solids carry sound. Another form of kinetic energy is the motion of waves of electromagnetic fields, which isn't a thing. It's a potential to release electrical and magnetic energy, and that's what light is, and also X-rays and radar and microwaves and other things that are related to light. And another form of kinetic energy is electrical current. We're very familiar with this in our culture. We plug things into the wall all the time. Tiny charged particles, electrons in wires, moving around are electrical current. So as they move, they store energy, and so we use that to run things. Another way that energy can be stored is in the positions of objects with respect to each other. Like here, consider these two magnets. If I move the magnets apart from one another, what happens is there's a force that's going to pull them back together as long as the North Pole and the South Pole here are aligned with each other. So if I let go of them, well, they snap back together. Work has been done because you've moved those objects, and even temperature has been increased because where they smack together, it's going to get a little hotter. So energy was stored originally in the positions of those two magnets that they were held apart from each other. Energy that's stored in the positions of objects is sometimes called potential energy. That's the name we give for that mode of energy storage. The magnet example that we just saw is an example of potential energy. The positions of the magnets with respect to each other stored energy. This would also be true if you were to put two south poles or two north poles of the magnets together and push them together. That positioning would also store energy in the system. Gravity is another example. Every two objects in the universe are attracted to each other by a force. Here's how this works. I take this one object here that has a mass 1, and a second object that has a mass 2. the force of gravity between these two objects is equal to a big number that we don't have to know, it's a constant, times the mass of the first object times the mass of the second object divided by the square of d, which is the distance in between the two objects. So if I look at this equation and analyze it, it tells me that as long as the two objects have mass and they're somewhere close to each other, there's a force that pulls them together. Now, if the two objects don't weigh very much, like if you and I stand next to each other, that force is going to be very, very small because we're not very massive. But if you and the Earth stand next to each other, because the Earth is so massive, there will be a pretty significant force between the two of you. So in this example, if you're standing on top of a cliff, this guy who's up here has a lot of energy stored in him because this force is pulling him down, but he's positioned away from the center of the Earth. If he jumps down to the bottom of the cliff, his potential energy turns into kinetic energy for a bit, and then it gets dissipated as work gets done at the bottom. Obviously, he's been worked, and he no longer has stored in him that energy of position that he had before. There's an invisible but very common form of energy storage that's made up of the positions of very, very tiny objects in substances, objects like atoms and ions and molecules that we're studying about in chemistry. The positions of these tiny objects with respect to each other is chemical potential energy. So energy is stored in the positions of tiny objects. Chemical potential energy can be stored in chemical changes like photosynthesis. The energy from the sun goes into the plant. The plant stores that energy in the positions of atoms in sugar molecules. When you charge a battery, chemical potential energy is stored in the positions of little ions inside the battery. When you eat food, you're releasing chemical potential energy. You're using it up. You're turning it back into kinetic energy. So this guy's eating a sandwich or something like that. As he goes and runs or walks or does whatever he's going to do, he's going to respirate that food and release the energy that was originally stored in it from the sun. Chemical potential energy is also used when you discharge a battery, like this flashlight. The energy that was stored in that battery when it got charged is released when the battery shines. When you burn fuel, the chemical energy that was stored in that fuel originally from photosynthesis, that is now released as the fuel is burned. Now there's a law about all this releasing and storing of energy called the first law of thermodynamics. Now remember, a law is something that we haven't ever found an exception to it. So this is a generalization that's so true that we call it a law. We just say it's always this way. The first law of thermodynamics says this: energy cannot be created or destroyed. It just changes forms. So the first law of thermodynamics is saying the total amount of energy that's in the universe is the same as it's always been and the same as it always will be. So this brings up a question. You constantly are hearing about the energy crisis, or how the world is running out of energy. How is it even possible for us to be running out of energy if the first law of thermodynamics is true? We can't run out of energy because we can't destroy it, just as we can't create it. Well, the answer is found in the second law of thermodynamics. The second law of thermodynamics says this: whenever energy changes forms, some of that energy is changed into a form that can't do any work anymore. So basically what's happening to us is we are slowly having all of the energy that's available to us for doing work turn into heat energy, which can't do any work for us. The second law of thermodynamics brings up a concept that you might have heard about in other classes called entropy. And entropy has to do with how disordered the energy storage is. Here's an example that might help you understand the second law of thermodynamics. Here's a car. This car has got a full tank of gas, and it's about to go 500 miles. So the driver starts it up, the tank of gas is full. All of the energy right now is chemical potential energy that's stored inside that car. And then the guy begins to drive. Well, most of the energy that's in that tank of gas is actually going to be dissipated as heat energy out of the radiator. In a car, typically about 80% of the energy is lost, and about 15% actually moves the car down the road. One of the other ways that energy is lost, besides through the radiator, is through friction. The wind resistance going past the car, and also the friction between the tires and the road, that's a heat loss. So the energy that's lost in that way does not get you down the road. If he's driving at night, the electromagnetic radiation, the light that comes out of his headlights, is another loss of energy. If he sounds the horn, that's sound waves. And just the engine noise and the tire noise of going down the road releases some energy. That's kinetic energy release of some of that potential energy. And then when he finally comes to a stop at the end of the 500 miles, the friction between the brake drums or rotors and the pads or shoes also releases a little more energy as heat. So at the end of 500 miles, where is the energy? It's still there. It's now heat energy that has slightly warmed up the road over the past 500 miles. And it's not recoverable. You can't use it to drive your car again. And so that's where the energy crisis comes in. It's not that we don't have as much energy as we've ever had. The problem is that the energy is less useful to us, and that's what makes it a crisis. Well, in the next video, we're going to talk about matter and get kind of more to the heart of what we're interested in chemistry.